By the end of the last episode, we had followed the evolution of a massive star to its final stages. We saw that the structure of matter itself can resist compression. In some stars, that resistance can halt collapse and produce a white dwarf. Under even more extreme conditions, matter can assume an entirely different state and produce a neutron star. But these remarkable properties of matter have limits. For sufficiently massive stars, there comes a point at which no known process can prevent continued collapse. What happens then? The answer emerged from Einstein's theory of general relativity, and the result was one of the most surprising predictions in the history of science: a black hole. In 1915, Albert Einstein introduced general relativity. It was not simply a new theory of gravity, it was a new way of thinking about gravity. Newton had described gravity as a force acting between objects. Einstein described gravity as the curvature of space-time itself. Only months later, Carl Schwarzschild found an exact solution to Einstein's equations. He did this while serving on the Russian front during the First World War. The solution described something extraordinary: a region of space-time so intensely curved that nothing inside it could escape. Not matter, not even light. At first, this seemed less like a real object than a strange mathematical possibility. But the mathematics had opened a door. And once that door was open, physics would never quite be the same. For decades, black holes remained controversial. Many physicists regarded them as strange mathematical possibilities rather than real objects. But evidence slowly began to accumulate. One of the most important early candidates was Cygnus X-1. Astronomers observed a massive visible star orbiting something they could not see. Material from the visible star was being pulled toward the unseen companion. As that material accelerated, it heated to extraordinary temperatures and produced intense X-rays. The unseen companion had too much mass to be an ordinary star, and yet it produced no visible light of its own. By the early 1970s, Cygnus X-1 had become one of the strongest candidates for a real black hole. When I was studying physics as an undergraduate, black holes were still not universally accepted. Cygnus X-1 was one of the objects that began to change that. General relativity predicted more than black holes. It also predicted that disturbances in space-time itself should propagate outward as waves. Gravitational waves. Recall back in episode 1 of this season when I discussed a conversation I had with Kip Thorne during the early 1970s. At the time, Joseph Weber at the University of Maryland claimed he had detected gravitational waves using massive aluminum detectors. I asked Thorne about Weber's work. His response was immediate: there must be something wrong with Weber's apparatus. At the time, black holes were still controversial. Gravitational waves had never been confirmed. Much of this physics still existed at the uncertain boundary between mathematics and observation. Thorne seemed to think that something must be wrong with Weber's apparatus, and in the end, he was correct. But Weber's reported detections carried an extraordinary implication. His data appeared to suggest that gravitational wave events might be occurring far more frequently than anyone expected. If true, it implied a universe filled with violent astrophysical events, possibly involving black holes. At the time, many physicists found that difficult to accept. Over time, the evidence surrounding Cygnus X-1 became harder to dismiss. The unseen object appeared to possess too much mass to be a white dwarf. It also appeared too massive to be a neutron star, and yet it produced no visible light of its own. As observations improved through the 1970s, alternative explanations gradually began to fail. The simplest explanation remaining was extraordinary. Cygnus X-1 appeared to contain a real black hole. But Cygnus X-1 raised an even larger question. If stellar mass black holes existed, what about the centers of galaxies? At the center of our own galaxy lies an object known as Sagittarius A star. What you are viewing here is a visualization produced by the Max Planck Institute for Extraterrestrial Physics. It shows the motions of stars near Sagittarius A star at the center of the Milky Way galaxy. Astronomers discovered that these stars were orbiting something invisible with enormous mass, millions of times the mass of our Sun, compressed into a remarkably small region of space. The simplest explanation was extraordinary. The center of our galaxy appeared to contain a supermassive black hole. And over time, astronomers discovered something even more remarkable. Supermassive black holes appeared to exist at the centers of most spiral galaxies studied. The universe was revealing something far stranger than physicists had once imagined. What began as strange mathematical possibilities gradually became something far more profound. Black holes now appear to be woven into the structure of the universe itself. And yet, even now, we still do not fully understand what they are. General relativity predicts them. Quantum mechanics resists them. And perhaps that tension is telling us something important. Perhaps the real answer lies beyond the frameworks we currently use to describe the universe. In the next episode, we will begin exploring that deeper problem. If it is possible, it is mandatory. Come walk with me.